Our next speaker is Bho Matthiesen from University of Bremen. He has been working on communication theory, resilient communications, and non-hash networks, and he will be talking about resilient radio access networks, AI, and the unknown unknowns. So, welcome, Bho.
Hi. Say we have heard about how multifaceted resilience is. We have talked about policy, we have talked about technological enablers. This will be different. I'm focusing on something very narrow at the core of 6G, which are radio access networks. Most of what I say is not specific to radio access networks, but when in doubt, just keep in mind that I'm referring to radio access networks. Now, most of what I'm going to say might also be controversial to many of you, but that will be fun. So, I'm also ignoring the whole ecosystem around the RAN, because I'm just focusing on this narrow technical field. So, most of you will probably agree that we need AI to make our radio access networks resilient. We might disagree on the time scale. So I don't need to motivate resilience at all. I just want to point out two things. Recently I talked to someone from, let's say, not Nokia, and he said, well, actually, we could have made 2G networks resilient already. It's just a matter of cost. I might add, in this case, we wouldn't have had technical resilience, we would have relied on operational and organizational resilience. That means having humans in place and ensuring the resilience of the system. So when the ITUR now says that we want to have resilience in 6G, actually they say we want to have security and resilience, and this is enhanced capabilities from before, but resilience is actually new in there. So what they mean, I guess, is technical resilience, so resilience inherent in the system, not relying on humans alone. It also says, or tells us this picture, that security and resilience are two different things. Security is actually inherent to resilience, but it is not resilience. Robustness is also not resilience. There's something more. Resilience is not just all the components and enablers we have heard about today. Resilience is something more. And what I started with was the question, what is the essence of resilience, and what are the implications of that? So this is what I'm going to focus on, basically on the end game of resilience. What is a resilient system, instead of what do we have to do to make our systems more resilient than before? Now, if we have some arbitrary system, it runs at nominal performance, let's say 100%, and if we have a robust system, which is what we usually have today at most, is when we encounter a disruptive event, either the system can just handle it and continues to operate correctly, or it fails and hopefully degrades gracefully to some degraded state of performance, and it stays there until a human fixes it, or if we are lucky, until it restarts and the disruptive event goes away. Now, what can a resilient system do differently? Well, the first thing, and this is very similar to what a robust system does, is it remediates the impact of the disruptive event. Might take some preemptive actions, whatever, so some additional intelligence to robustness, but mostly the same. And then comes the core functionality. It autonomously heals itself. It recovers from the disruption without human intervention in the least amount of time, if you want to measure this. There's another dimension, a long-term dimension, which is that the system should also learn from what it encountered and evolve. This is even harder to do than the autonomous recovery. And some colleagues also hope for improved performance from this. I think it's science fiction, so I'm not going to bother with this today, but some people talk about this. Now, I said I wanted to get down to the essence of resilience, and I like to approach this from a system design perspective. So when we build a new system, the first thing we do is we make it work. Next thing to do is to make it reliable. That means we narrowly define the nominal operating environment, and then we make it perform with high reliability, meaning low probability of failure in this environment. Once we're happy with that, we start talking about robustness. Robustness can be seen as just extending the nominal operating environment to off-nominal conditions, like saying your car should be able to operate up to minus 80 degrees instead of minus 40, which might be the nominal operating environment in Finland. So after that, we can talk about resilience. And what is left is to remain operational under unanticipated conditions. And if we consider robustness already to handle known unknowns, meaning we know what effects can target our system, but don't know which values they will have, what realizations they will have, then it's a stochastic perspective towards your system. So when you put resilience on top, this is very low probability and very high impact events that are externally caused. It's not inside your system. And referring to this picture below, the environment your system might have to operate in after a resilience event might look completely different to the environment before. Think World Trade Center, think a bomb, since we are talking about military communications so much today. So one can say that robustness is about known unknowns. We know the effects, but we don't know what they are, while resilience is about the unknown unknowns, things we do not know before the fact. Another name for this is black swans. They are rare and high-impact events, and they are completely unpredictable, while robustness deals with gray swans, known unknowns, somewhat predictable. Ultra-reliable communications can be seen as robustness. So a lot of the things we have heard today, they contribute to making your system way more resilient than before. But a war is something we can anticipate. We know that it's going to happen at some point in time. So one might argue that everything we do to address war scenarios is robustness. So a resilient radio access network, to break it down, to make it simple, has three components. A system architecture that is really flexible, that can be reconfigured. Situational awareness, our system needs to know what's going on, and it needs to need to have way more situational awareness than it typically has. And the key aspect is autonomous control. So without autonomous control, we can't reconfigure the system, we can't create it, or we can't use the situational awareness. And coming back to my earlier question, what's the difference between making something more resilient versus a resilient system, is a resilient system has to go beyond robustness to call it rightfully resilient. And at the core of this is autonomous adaptation to completely unanticipated conditions and self-organized evolution. And the last one might be really hard to pull off, so let's say assist the human operator as best as possible and be evolvable at least. Okay, I'm going to focus on the autonomous control. And I'm not an AI researcher, I'm a communications theorist, but we are going a bit deeper into AI now. This is the model I'm using for a radio access network or any other system. It's a model, a general model of an intelligent decision maker. It's not by me, it's from Sutton. He is famous for reinforcement learning. So we have some decision-making agent. Agents could be a scheduling functionality, distributed beamforming. It can also be the complete control logic for a flying base station. This decision-making agent interacts with the rest of the world, other systems, everything. it gets observations, it executes actions, and it might get some reward for actions which are generated outside the agent itself. What I'm going to assume here, because I want to talk about AI, is that this agent has to be implemented as a learning machine, more precisely as a statistical learning machine. That is deep learning, large language models, GPTs, everything we are talking about when we say AI today. The world can be modeled in the most abstract way as a probability space. This is a huge probability space. Don't try to imagine it. And the nominal operating environment is a small subset. Now, if you have a major impact disruption, that's the one we are interested in, it's a transition to a disrupted environment, meaning there's a city, and then there's no city. That's a disruptive event. We transition into a completely different way, part of the probability space. Okay, as a first approach to this, let's assume we have a complete mathematical description of this world probability space. That's completely unrealistic, but just assume it for a minute. Now, every statistical machine learning tool trains over some loss function, and it minimizes a risk functional, usually the average. Mathematically, that's this nice formula that covers every possible case. Now we have a rare event. This rare event means it has a very low probability of occurrence, and we can say that the probability mass of the disrupted environment, that's the red area, is very small. Now, we know from measure theory that if we integrate over an area with zero probability, the integral over there is zero. But what happens if we get very close to zero? Now, the hope is we can find some magical loss function to cover all these low probability events we are interested in. No. There is no rapid drop-off. It's a very good-natured convergence to zero as the probability mass of the disrupted environment goes to zero. That means we cannot find a magical loss function that addresses all our unknown unknowns. If we have some low probability event that we know about beforehand, we can design our loss function to handle it. But if we don't know about it, there's no way we can find a nice loss function that covers all of these events. So statistical machine learning is not a magical bullet. Sorry. Now, that was a completely unrealistic worldview. Let's make it a bit more realistic. Of course, we cannot observe the whole world. So our system operates on beliefs. That means the world is only partially observable. Speaking of me, I can observe this room here, but I can't see more of the world. Same holds for any technical system, of course. Also, sensors have limited perception or limited resolution, so we get a heavily downsampled and smaller observation space from the real world. Mathematically, it's like saying the cardinality of the observation space is much smaller than that of the real world. As engineers, or we can expect engineers to design the observation space such that it is adequate to, it's an adequate representation of the nominal environment we are interested in. And the real probability of the real transition probabilities of the world induce some probability distribution in this observed world, and that is what your machine learning model usually learns. Now, if you have a disruptive event, what happens is we transition to a completely different part of the world in probability, and if we have our very limited observation space, what happens is that this observation space, or this disrupted environment, is mapped to the same region as the nominal environment. So the only difference the system will see is a shift in the probability distribution it observes. So what does this mean? The probability distribution we have learned before, or we have optimized our system to before, is different to the one we are seeing now. And there's a thing we call the no free lunch theorem in machine learning, and it says adaptation is necessary to remain optimality. So if we see a heavy distribution shift, we cannot expect our previously trained model to be optimal. that means we have to do online learning. So we have to do continuous adaptation to domain shifts if we want to make our system resilient. Now here's the problem. This is how we implement most of the continuous learning approaches today. That's model-free agents. Reinforcement learning is mostly model-free. Model-free agents gain experience through experimentation. That means if your world changes, you have to run a lot of experiments to get the new experience, which you can then incorporate into your agent. You don't want your system to experiment in an emergency situation. This is also only reactive control. You cannot plan if you just observe the actions of your immediate step. Another thing these model-free agents struggle with heavily is domain adaptation. In general, they learn very slowly. You need to train a reinforcement learning agent for a very long time. And there's very strong experimental evidence that even the most powerful reinforcement learning approaches we use today, which is deep Q networks and PPO, struggle heavily with severe domain shifts. They cannot adapt to this. It's basically learning from scratch. The opposite are model-based agents, and yes, there are reinforcement learning agents that can do this. You need a model to do planning. So what's the difference? You keep a transition model. It's not really a world model, but a world model serves. If you have heard this word. So you have an internal model of the world you are interested in. And when you gain some real experience, you can use it to improve your model. But then you take your model and you run your basic reinforcement learning algorithm or whatever on this model for controlled search over simulated experience for some time, and you evaluate different plans. In control theory, they call this model predictive control, which is a very good word for it. I like it. It's optimization. This is where I come from. Anyhow, if you're happy with your plan, you execute the plan, you observe some actions in the world, and then you get real experience, update your model, and so on. So trustworthy autonomous recovery requires this planning. Planning requires an environmental model, so we can conclude continuous learning with model-based agents is strictly necessary to achieve resilience, at least in the long run. I'm not saying that statistical machine learning is not helpful. It is. But for the end goal of resilience, it is not. Now, we still have the challenge to adapt our model to the domain shifts. That's now in the domain of transfer learning. Just to say this much, a positive information transfer between two distributions is only possible over distributionally invariant features in your model. And those can be interpreted as causal effects. Now, causal effects go strictly beyond statistics. And that shows us that we might need to look into causal machine learning. Now, to conclude, or almost conclude, resilience needs continual learning. This fast adaptation to change conditions is basically retraining, and that's the core challenge here. Model-based AI might help with that. It is also necessary to do actual planning. In general, resilience, the core of resilience, will require AI with cognitive capabilities way beyond inductive inference. Inductive inference is what animals do. I see the owl sees a leaf move, so she attacks to get the mouse, to have lunch. But this is only the lowest level of cognitive capabilities. Mathematically, there are two further levels above this, which is the interventional level. What if I do, and how do I do it? That's imagining what's going to happen, that's planning. And even beyond that is counterfactuals, where we come up with theories for what happens, and these are the capabilities we need to evolve autonomously. So in the long term, we're looking at narrow human-level AI. So this tells us resilience will not happen until the AI people get their stuff together and advance significantly beyond where we are today. This brings me to the questions, what can we do as communication engineers? I mean, I'm not an AI researcher. I want to work on resilience. ITU tells me I have to do this. So what we can do is we can prepare our network for autonomous control. We can make our networks way more robust and flexible. Loose coupling is one keyword. When we design algorithms, we should have resilience in mind. I think resilience is a complete different design methodology that we need to apply to our systems. There's great papers written by colleagues about this. When we use machine learning, let's try to use model-based learning. Let's try to bring some causal knowledge back into the systems and not be purely data-driven. And last but not least, we have to strive for cost-efficient solutions, like NTN networks, like joint communication and sensing for situational awareness. Yes, that's it. I mean, 6G will not be a resilient system, but it will be more resilient than what we have today if we do it right. It's a marathon, not a sprint. Thank you.
Yeah, I want to first of all thank you. This was really, really an amazing presentation. I mean, a lot of great insights and new ways of looking at things. I have one question. If we go to the model-based approach, or the one from Sutton's book, the figure that you showed about how reinforcement learning works, and when you would it's all right. So you showed that there is a distribution shift from the kind of world that we observe to a different world due to a disruptive event. What if we have an adversary that shifts the distribution of the reward and not the world? Because that is the kind of world sometimes communication systems can see if there is an adversary where they shift the distribution of the reward.
Yes, that's a great question. I have consciously ignored this because it's partly security, but it's a great question. I mean, what I focused on is non-malicious events as opposed to what we need to do when we talk about man-made events. Once you bring man-made changes into it, malicious changes, then it's very clear that you need to have an AI that can operate on human levels to counteract this. And we are not there yet. I mean, ChatGPT and how they are all called, they are very good at certain tasks. They're much better than humans. But it turns out they are only better at some tasks. And they cannot even remotely approach human creativity. So it's just that these tasks these models are good at are very difficult for humans. And that's why they are so impressive to us. But once you really have to fight against a human opponent in a partially observable environment, chess and Go are not partially observable. You can observe them completely, you know the rules. That's not the real world. And they have no chance against humans right now because that's not what statistical machine learning is good at. Thank you.
All right, thank you, Bho.
Thanks.
Thank you, Secretary.